Okay, Dashers. Today we are talking about wave properties. So some of you will have, maybe you chose to do the gizmo first, and then you can pretty much fly through these notes. Or if you're doing these first, then I think the gizmo is going to go fast for you, but maybe it doesn't hurt to see these vocab words twice. If you've done some of these, if you've covered some of these vocab words in math, then what you're really listening for is what's different about the way we use this word in physics. Okay, so for a wave in physics, we are talking about just a disturbance that travels through matter or space. If you ever see a question like, what is a wave made out of? That is a trick question because a wave isn't made out of anything. It's just energy that's being transferred or transmitted through space. Okay. All right. Then, oops, I'm going to go kind of quickly through here, but in this class, we're going to start off talking about mechanical waves. So when I say mechanical, I just mean this is the kind of wave that needs to have some stuff to go through. Okay. So in a few minutes, I'll show you my daughter and I making a little wave in a slinky. So that's an example. And here, when you see the word medium, these require a medium to travel through. I always think of like how a psychic, I don't believe in that, but if you did believe in psychics, they are sometimes called mediums because, they're the means that, you talk to somebody who's one of your past relatives that's died and gone to heaven or something. But that's what we're talking about. It's the stuff that the wave gets to travel through, okay? So we're thinking Whoopi Goldberg in the movie Ghost, right? All right. So then the two kinds of waves we're going to demonstrate, but transverse waves, the particles will go perpendicular to the way the wave actually travels. This is the kind of wave that you would do at a Badger game. So the wave goes around the stadium, but the people who are the particles doing the wave stand up and sit down, okay? So if you think about it, the wave, the disturbance goes around, it goes sideways, but the people, the particles stand up and sit down. That's perpendicular, okay? Then in a longitudinal wave, the particles shake parallel to the way the wave moves, but they just don't go very far. They just shake back and forth, okay? So let me pause here and we're going to show you two, the examples of transverse and longitudinal in a slinky, and then you'll see it in the gizmo as well. Okay, first we're going to make a transverse pulse. Okay, go ahead, Mary. Okay, so hopefully you saw the pulse went from her hand to my hand, but the little hair tie went perpendicular to that. Okay, now wait, let me stretch it. Works better this way. Okay, now do the longitudinal pulse. Okay, thank you, Mary. Okay, so then if we're talking about water waves, those are really complicated because they would really be a combination of longitudinal and transverse, which you can kind of see if you look at this picture here, where the water at the surface is doing like a circular motion. Okay. All right. And then as far as the vocab goes, when we're measuring waves, there are lots of things we can measure about them. One of them is wave speed. Okay. So if you are watching a particular wave crest, how long does it take to get, say, from the stern of your boat to the beach? okay? We can do that with distance over time. And that depends on the medium, the stuff that it's traveling through. Nothing else. Oops. Amplitude, we've talked about before. We talked about that on Monday, okay? And then that sort of sets somewhat the energy of the wave, okay? Then wavelength is a characteristic that you've probably measured in math, but I'm not sure you called it wavelength. So it's the distance from one peak to another peak. In physics, we call them crests, or you can measure it from a valley to a valley. In physics, we call it trough to trough. We're using the variable lambda to represent wavelength. It kind of looks like a wave, okay? You get to practice drawing that variable. And this variable is sort of the most dependent one. It depends on a few other variables like wave speed and frequency, okay? And then if you're labeling, okay, we have some labels here for you to add, so you can pause this video and label it. Be careful that you label what's on the x-axis, okay, because it's not, this one has a distance on the x-axis. That means that this is wavelength. We're going to get to that in a minute. There's another kind. Then I'm skipping over a slide. Okay. And then period and frequency, we've talked about period. Frequency is just the reciprocal of that, okay? So I think it's because people don't like fractions very much. Usually people give the one that's not a fraction, okay? So usually if the period is really short, people would rather just say the frequency. They'll say, okay, it's 60 hertz or 60 cycles per second. Then if the period is long, okay, like if some of you were measuring the period of the plate in your microwave, that's kind of a long one. So it's in seconds. So you wouldn't tell me how many times per second it rotates because it doesn't even do a full rotation in a second. So you would probably give me the period instead because that's more than one, okay? But these two are reciprocals of each other. I did, just for today, wear my, let me change the angle, my Hertz shirt, which gives, you know, it looks like a Heinz shirt, but it's cycles per second. Okay. Just for you. Okay, then what's left here? We've got the two equations, which are just reciprocals of each other, okay? And then just remember that these two variables depend only on what's making the wave in the first place. Who's doing the shaking, okay? What is making the wave? That is what sets period and frequency. It can't be changed after that, no matter what that wave goes through. Okay, so then here's our last bit. We're going to stop for today. And I want you to take a look at these carefully, pause the video. And in fact, I'm going to pause and switch screens so I can write on this screen. Okay, so I'm going to give you 10 more seconds to identify the difference between these two graphs. Hopefully you noticed that they have different labels on their x-axes. So this one's labeled with x in meters or position in meters, and this one's labeled with time in seconds. So if you are imagining like several waves now, maybe you're thinking of the gizmo if you already did it. This would be a snapshot in time of the wave on the gizmo, so that you could measure how far apart the crests are, okay? Versus this second graph, would be tracing where is a particular location of the green dot in the gizmo as time goes by. Or thinking about the slinky for a second, where is the hair tie on the slinky? If we watch just the hair tie shake back and forth and back and forth. Okay, but in any case, you need to be able to read these graphs. So let's measure the amplitude. That's the same on both. I always measure from 0, and I measure up to the highest height or down to the lowest valley. Now this should be labeled with a negative sign, but I take the absolute value. So this would be 0.2 meters. Which graph shows the period? Well, the one that has time. And what is the period? Not 5 seconds. Don't just read off the maximum, okay? We need to know a full cycle. So usually I would try to pick from a crest to the next crest. That happens to be 2 seconds, okay? If you're gonna start at 0, like if you started here, that's fine. But you need to remember to get a full trough and a full crest. So you'd end up going from 0.5 to 2.5 on the time scale and subtracting 2.5 minus half. Okay, which graph shows the wavelength? This one here. So when we look at the wavelength now, we're looking for the length of a single wave, crest to crest or trough to trough. So it's convenient. This one has a crest at 0 and another crest at 4. That would be 4 meters, okay? Or I could look here at trough to trough from 2 to 6 gives me 4. Now, frequency, I will need to calculate. So, I could see how many waves happen in 1 second. That's the definition of frequency. But I could try to estimate that. I think it's easier just to do the reciprocal period. So 1 over t. That would be 0.5, and the units again are hertz. And then tomorrow we'll get into how to calculate wave speed if you know these things. Okay.